So, hi, welcome to my talk. I'm Martin Hořeňovský. I am Senior Software Engineer at PEX, and today I have talk about introduction to floating point numbers as users. We will not try to go super deep into their theory and so on, only we will try to use them. So let me actually start with some disclaimers. First, I will be using floats as short for floating point numbers because saying floating point numbers over and over and over again is not fun. Now, I will be talking about IEEE 754 binary floats. One, IEEE actually contains decimal floats as well. Two, there is a bunch of other floats that exist, and we will not touch these because they are mostly unused unless you are one of the poor people who has to use IBM. Right? Now, we will not go into the full details. We will look at them as users. We will look at how to use them to accomplish our goals, not, anything else. And I want to start with a quick quiz. So we have an assert, and we say, okay, so 0.1 plus 0.2 should be equal to 0.3. Will this pass? Or will this fail? So I have voices for fail. Yes, this will fail. We have all seen this example at some point. Another example. We have 20 million as a float, plus 1 is equal to 20 million. Will this pass or fail? Pass? Okay, and fail? I have 1, 2 votes for fail. It will pass. 20 million plus 1 is equal to 20 million. This makes perfect sense, right? So you know what? Let's go overboard a bit. Let's say 20 million plus 1 is equal to 1 plus 1 plus 20 million. Again, pass? Is this true? Or is this false? I have some votes for false. This is false. 20 million plus 1 is not the same as 1 plus 1 plus 20 million. So the thing is, right, what the hell? But it makes perfect sense. It actually makes perfect sense if you understand how floats work, right? And I want that after we leave here, for you to be like, yeah, this makes perfect sense. I know why. I know how. So yeah, this should make sense to you after we leave. And I spoke about understanding. The thing is, our tools don't always help us. Like this is simple test in catch 2. We have some test case, that's not important. Important is that we have double, that's exactly 1. And we say, okay, give us the next double that's larger than 1. And we ask, are these equal? Well, they are not. And we will be told, this failed. A equals because B has failed. They are not equal, this is fine. And we will be told that the numbers were 1.0 and 1.0, right? The tools don't always help you. I am kind of responsible for this one, sorry. But I can't change it. Backwards compatibility. What do you do? Well, so contents, what we will be actually talking about today. I want to start with decimal floats. I said we were talking about binary floats. So why decimal? Because my theory is that the issue people have with understanding floats is that we go from decimal to binary because we are used to computing stuff in decimal. We do math in decimal. And we have to go to binary. And we are used to like perfect math, and we go to floats, which have their own rules. So instead of making these 2 steps, we will make one. Decimal floats. We will learn how they work, why they work, and then we will go to binary floats. And we will figure out what actually IEEE tells us about floats, what guarantees they give us for math when we do it. And then we actually learn how to compare floats, because after we compute something, we now need to know whether, for example, we computed what we should have, whether we have hit some threshold of notability for an event that we have to trigger. And finally, we will learn that actually we learned nothing, nothing works, it all breaks down at the end. So why are floats weird? Why did we get something as weird as floats? Because we have design constraints. Every decision we ever made has some design constraints. This is no different. Our big constraint number 1, floats have to be usable for computation in real numbers. And real numbers are annoying. Not only are they infinite, this is easy, they are uncountably infinite. This is hard. For example, ints, they cover whole numbers. Whole numbers are countably infinite. This is easy, right? Then next constraint we have, the floats must support both tiny and large numbers, and they must support it in one operation. Right? We have this tiny number, and this is a huge number. And we must be able to multiply them together and get an answer that makes sense. By the way, does anyone know what these numbers are? Okay, these are from physics. The first one is the gravitational constant. The second one is the mass of the sun. So I'm quite literal that you must support these two in one computation. You will multiply them. You will quite, like if you do physics, if you need to compute something with gravity, you will multiply these two numbers. And the last constraint, the one that always makes issues, we want to be efficient in hardware. So the representation has to be fixed size, computers like fixed size, and it has to be relatively small. We can't burn too much hardware on just floats. So what do we do about this? Well, before we go there, let's do the decimal floats, as I promised. And actually, let's do something else first. Scientific notation. I hope that we have all heard about it, but the basic idea is that you have some number, m, you multiply it by 10 to some exponent n. Right? This is scientific notation. We all use it in school at some point. And then you can normalize it. You can say, but I want m to always be between 1 and 10. Right? This means that I will always have only a single digit before the decimal point, nothing else. That's all we require. We then get numbers that look like this. They have one useful property. It's super easy to compare them. Like you see, okay, this is down to the power of 7. This is larger than the other two. We don't have to think anymore about it. Now, let's say that we said that we need fixed length stuff for hardware. So let's say that we actually say that scientific notation has to have fixed length, right? So we say, okay, so we use some x, 1 digit before decimal point, 3 digits after, 1 digit for the exponent. Well, and what about negative numbers? For now, let's not bother. Let's say that the minus sign is just stored separately. And for negative exponents, the same. By the way, we need negative exponents, so we represent small numbers. Right? Negative exponent, small numbers. And that's floating point format, just in decimal. We just made one. Okay? This, when we look at it, the first part, the x, y, is called the mantissa. These are the digits that we have of the number, that we know that are there. And z is the exponent. That's the magnitude of the number we are handling. Okay? Now, this little format we made can represent numbers in this interval from minus 9 billion, 999 millions, blah, blah, blah. The important part to notice here is these zeros, right? These are zeros, not nines. Why? Because we already don't have the digits in the mantissa to have anything else. And that's the whole thing about floats. We have limited number of digits of precision. So we then just have to round these into something. Okay? Now, the smallest positive number we can represent is this. As I said before, negative exponent means tiny number. I am not going to try to read this. That's too much for me. But is there another option? Can we have smaller number in this format? Well, the answer is yes, maybe. So we can denormalize the number. We can say, okay, but what if we say, but I actually want to allow myself to have 0 at the start, and I'm fine with just having the 1 here. We have just gained 3 orders extra that we can basically get close to the 0. Notice that we have 3 more zeros here. Now I have absolutely 0 chance of reading the number. But the trade-off we made is that we no longer have the number normalized, and it's more complex to use it for us. Now, IEEE flow does exactly the same trade-off. It says, most of the time, my mantissa is normalized, easy to work with, and you get some number. In special circumstances, it's denormalized, and you can get closer to 0 at the cost of slower operations. I equals the normal numbers. And I know that historically, lots of applications used to turn them off because they cost performance. It's getting better. But the point is, this gives you extra precision around 0. Now, another interesting thing about floats that we can easily see in this format is that the absolute difference between two numbers that are closest to each other increases when the magnitude increases. But the relative difference is the same. Example to explain this. Right, we have these two pairs of numbers on the top and on the bottom, and they are all like as close to each other as they can be. Right? This is just the difference is 1 in the last place that we can represent. And when you take the difference, now in absolute numbers, this is 1. This is 100,000. This is massively different from each other. But in relation to the two numbers we subtracted, they're exactly the same. That's what I mean. The relative difference between two closest numbers is always the same, while the absolute difference just scales with the magnitude of the numbers. Now, we made this design in like 3 minutes, so we have issues. Right, so one, we have both positive and negative 0. We said we store minus sign somewhere else. This means that we can have both negative and positive 0. We have lots of representations for 0, right? We have 19 actually. They look like this. We just set it 0, and then we just pick whichever exponent we want. This is a little bit of an issue. We can handle it in some ways, like say there is one canonical format for 0, or we can just assign meanings to some of the representations. Right? For example, we can say if we overflew our little float, if we have number that's too big, we will pick, say, this representation and say that's actually infinity. So we can use the encoding space that we have there. And negative 0 has another 19 ways to represent it. We will somehow handle it. Infinities, we can use it for errors, so on and so forth. And here is the part that's important. The decimal flows are just as weird as the binary ones we started with. Right? We get this fun fact, like 1.9 times 9 is not 1 if you do the computation in decimal floats. Okay? 10,000 plus 4 is just 10,000. 10,000 plus 4 plus 4 is not the same as 4 plus 4 plus 10,000. Okay? And this is where we have to build the intuition for why this happens. So why is this true? Well, let's compute it first exactly. So we get, well, it's 10,004. Okay? Let's go to decimal floats. It's 1.0004 times 10 to the power of 4. But we have only 3 digits after decimal point. We have to do rounding. And 10,004 is closer to 10,000 than to 10,010. So rounding. We have to deal with rounding. And that's the issue. And this applies for this as well. The issue is again in the rounding, right? Because ideally, 1/9 is just 0.1 repeating. This is a little notation we use for the fact that we can't actually stop writing ever, or we will round down. But we have to round down. Right? To get to fixed number of digits, we have to round down, so we get this little number. Now, if we multiply it, we get 9.999 times 10 to the power of minus 1, which is definitely not 1. Right? These two numbers are no longer equal, because we rounded off the repeating part, because we don't have anywhere to store it. And the same goes for the last example, right? Summation goes left to right. So let's go through this. So this is what we start with. Now, next step, we added 10,004. 10,004 is 10,000. We just did this. And here, 4 plus 4 is 8. This is simple. Next step, well, 10,000 plus 4 is still 10,000. This hasn't changed. But 8 plus 10,000 rounds up we are now at 10,010, and thus they no longer can be equal. Okay? So quick recap. So once you are in floats, your additions and multiplications are not associative. You can't just change order in which you evaluate them. This will change the results. Then floats are weird or unintuitive in every base. You just have to play slightly with what is weird about them. I had to use 1/9 to get out of base 10 numbers to get the weirdness, but they will always behave weirdly. And of course, the issue there is, again, we want fixed type representation for an uncountable infinity. Are we all good with this? Well, then let's talk binary floats. So their base is 2. They are binary, right? This is like overview of how many bits they allocate to which part, mantissa versus exponent. This is not really important to remember in most cases. I just want you to notice that actually the number of bits in exponent grows for wider floats. This is not true for all formats. This is for IEEE. For example, hex floats in IBM don't grow. This has some implications for how they behave. And so we have some idea, like the smallest positive value for 32-bit float is this, 1 times 10 to the power of minus 45. This is small enough to represent the gravitational constant with a lot of reserve. And the max value is this, which is much larger than the mass of sun. Yeah, safe. And when we go to the 64 bits floats, so usually double in C, and we have ridiculous range between them. Okay, now the cool part about IEEE is that actually for a lot of operations you can make, you have guaranteed results. Right? If you do addition, subtraction, multiplication, division, and so on, you are fine. You will always get the same results from the same operation on the same two numbers on different computers and platforms, if they actually follow IEEE, right? This is always like little asterisk. They must follow the standard. So this is good. But this is different from getting useful results. Repeatable, correct results are not the same as useful. Okay? Let's go back to this. Right? This is not correct. It's repeatable. This is correct in floats. It's repeatable in floats. It's not useful. Right? So how do we fix this? Well, there is this naive idea. It actually works in most cases, right? Just sum the small numbers first. The issue is in the round off. So take the small numbers, add them up together, you get bigger number. Round off is less of an issue. This works pretty well in a lot of cases. So, don't knock it. It's okay to start here. But I want to talk about better tricks, which is Kahan summation. This is an algorithm you can just use, made by the same guy who actually came up with the IEEE standard. And it will fix this issue. It will give you the correct results for the example 20 million plus 1 in both cases. Okay? The cost is that it's, I think, about 3 times more computationally expensive to compute than just summing up the numbers naively. And there is one more issue. It doesn't fix everything. Right? If you get something like this, it's kind of silly, but it shows the problem. Right? 1 plus huge number plus 1 minus huge number should be 2. Right? But naive summation gives you 0 for obvious reasons. This is so huge that this rounds here. This will do nothing, and this will then just subtract everything. But Kahan summation actually runs into the same issue. It boils down to the fact that it assumes that your running sum is bigger than what you add in. If it isn't, it will break like this. Again, you can fix this. There are options that cost even more computations, but will give you the actual result properly. By the way, before I go to multiplication, what about subtraction? What do we do if we need to subtract numbers, not add them? Well, is subtraction different than addition of negative numbers? No. So there is your answer. Let's go to multiplication. So here's an issue. There is no good way to solve multiplication. You have to do it yourself. What you need is you need to somehow normalize your numbers, your domain you are working in, down to 1, to these nice numbers, small numbers, so you don't get runaway issues with the order multiplying away from you. And after you're done with the computation, transform it back. How? Depends on what you are writing. I will give you one example, but another option is to look for different way of computing the stuff you need. And okay, so example, to tell you what is possible. I used to do a lot of work with probabilities. Right? And probabilities are small numbers, sometimes really tiny numbers. And when you start multiplying them, the magnitude of your number starts going way down very quickly. You compute 100 probabilities, it's 0. So what did we do? Well, if you multiply numbers, it's the same as adding their logarithms. So we took logarithms of the probabilities. This gave us a much nicer number. We added them all up, and then we converted the number back to probability by taking the inverse. This is what we could do. You have to do something that depends on whatever you are working on if you run into this. Now, this is what we have guarantees for. IEEE does not provide any guarantees on transcendental functions, your sines, your logarithms, and so on. Definition of transcendental function is that it can be expressed as a finite number of additions, subtraction, multiplications, and so on, divisions, raising to power. Okay, you get the idea. There are functions that you can't really handle this way. Luckily, you can get implementations of something that's called correctly rounded math libraries. And it sometimes even works with okay performance. I'm not going to say good, I'm going to say okay, right? If you need repeatability in your sines, cosines, logarithms, and so on, download one of them, use them. Beware, they have issues. They are work in progress and research projects, and you will run into issues likely. So to recap this part, so basic math operations that we are used to should be reproducible. Caveat, must follow IEEE standard, must follow it correctly, blah, blah, blah. You can reduce numerical errors in your computations, use the right approach to what you are computing, and the simplest approach is always to use wider float, right? Do you have issues with 32-bit floats? Use 64-bit floats. Don't do anything else until you did this. Now, transcendentals are hard. That's one of the functions. Reproducibility is hard and slow. Okay? So this is a good time for questions about this part. Okay, we will continue. So now we have some numbers. We probably computed them correctly, maybe not, yes, maybe not, but we need to compare them because that's what we often do, right? We need to test whether we computed them correctly and so on. So this will be fun because there are 5 basic ways to compare floats. You can do bitwise comparison. You can do direct comparison. I don't think it has real name to it. You can do absolute margin comparison, relative epsilon comparisons, ULP-based comparisons. And all of these have some case where you want to use them and some downsides when you shouldn't use them. So you actually should know all of them, at least have some idea that they exist and why. Let's start with bitwise comparison. So it says that 2 floats are equal if their bit representation is the same, just forget they are floats. Now there are bit fields, compare the bit fields, you are done. This is not the same as what happens if you write A equals B in your code. This is different. Okay? And under bitwise comparisons, you have some fun stuff. First is that -0 and 0 are not equal. This makes some sense. It has some issues. And not a number, this is special error value, are equal, but they are also not equal. Because not a number has many different ways it can be represented. So if you do bitwise comparisons, it depends which representation you actually get. So this is the most niche comparison, the least likely you will ever need. So let's talk about direct comparison. This actually is what happens when you write A equals B. And when you use it, then -0 and 0 are equal. Okay? None is not none, never. None, not a number, is defined to not be equal to anything, including another not a number. And it's useful rarely. Only if you have pretty much exactly the case where you have like different implementation of the same stuff, and they should give the same result. Because then you don't want any like, then you don't want any margin for error. They should give you exactly the same stuff. It's like the main case where you use them, but actually most often it's a mistake if you do this. This is why compilers will warn you, and it's super annoying, especially because you are like, but in this one case, I am using it correctly. No, warning, fix it. So let's talk about absolute margin comparison. It's equivalent to writing this. You subtract the two numbers, you take the absolute value, and you check whether it's less than margin. In other words, you check whether the distance between the two numbers is less than some margin you have selected previously. Okay? Now, it has like pros and cons. So the big benefit of this, it's super easy to reason about. Like, I can give you margin 0.5. What does it mean? Well, two numbers are equal if they are within 0.5 of each other. This is easy. Like, my daughter can do it probably. And it does not break down around 0, right? 0 to 0.5, this makes perfect sense. This is good. Issue is that actually it's the same as direct comparison for large numbers. Why? Rounding, again. For large number, 0.5 rounds to 0. You are done. There is no margin. So, oh yeah, by the way, quick like fun fact. These are not actually equivalent for floats. Even they should be in math equivalent. Because the first one will reject two infinities as not being similar or equal, while the second one accepts infinities. Whether this is correct for you, I don't know. Depends on what you are doing. So let's talk about relative margin comparison. Our issue previously was that for large numbers, the absolute margin just decays to direct comparison. So let's fix it. Let's introduce some relative margin, some epsilon, that these can be different from each other, right? We say, okay, so we take the largest number, multiply it by some small factor, and that's our new margin. This scales nicely with large numbers. By the way, there is actually an alternative formulation. You can also use smaller of the two numbers. This behaves slightly differently, but that's not important. The important part is that when you do this, it's still easy to reason about, right? You can say, okay, 0.1, that's 10%. So the two numbers must be within 10% of each other. This is easy enough. It does not break down for large numbers. It does nothing for 0. If one of the sides is 0, or even just very close to 0, you are again in exact comparison territory. This time the issue is basically if you have 0 and you have 1, like then you would have to subtract 1 from the 1 to get to 0. So that's 100% margin. This is why it breaks down. So let's talk about ULP comparisons, or units in the last place. Basically, there is the idea that there is distance, ULP distance, and it says how far from each other two numbers are in the float representation, how many steps we have to make to get from one to another. Right? So, example, the distance of these two numbers is 0 because they are the same. Now, we changed the digit in the last place by 1, so the distance between them is now 1 because there is one step from 1 to get there. This takes 100 steps now because we have changed this 4 into this 5. Okay, so that's the distance. Brief aside, what's the distance between zeros, negative and positive? I don't know. It depends on how you define this. Just check with your library you are using for comparisons what they do here if you need this. Now, then the two numbers are equal if their ULP distance is less than the fixed number that you picked ahead of time. This is great, because it handles both 0 and large numbers gracefully. You say it's within 4 steps. Okay? 1 step, 2 step, 3 step, 4 step. For both huge numbers and tiny numbers, the relative distance is the same. And this is actually easy to reason about numerically, because I know if I add 2 numbers, I get at most this much error in the last place. This is great. Where does it fall down? Okay, I will tell you. These 2 numbers are within 10 ULP units. What do you actually know about the numbers? Nothing. Like, there is limited amount of people who can actually think at this level, naturally, and the answer is, I don't know what it means. I can tell you that I am close. I can tell you what pipeline guarantees I have, but I can't ever explain this to a customer. Right? Or non-technical customer has no idea what this means. Absolutely 0. So let's recap. First, there is no universal approach to comparing floats. There is a lot of them. You have picked the one that's right for what you are trying to do. Direct comparison is usually a mistake. Not always, but 90% of time, maybe more. You need to if you are using ULP distance, you need to understand what your tools actually calculate as the distance, right? What do they think is the distance between -0 and +0? What do they think is the distance between the largest number you can represent and infinity, and so on? Okay? So again, this is a good place to ask about this part. Well then, let's continue. I mentioned that I actually maintain catch 2, so I have a brief aside. What about catch 2? What if you want to compare 2 numbers there? You can use approx. Who here uses catch 2? Couple people. Who here used approx? You shouldn't be using approx. Sorry. This is what it looks like. You say, okay, something is roughly approximate to something else. It's absolute margin comparison, relative margin comparisons, and it's legacy, and you shouldn't be using it. The issue is that the relative margin comparison is this weird, not standard comparison that's not something that you can really reason about. What you should be using is matchers, because that looks like this. You can say, okay, I want pi to be within some relative margin of 3.14, and then you have also within absolute margin, relative and within a ULP margin. And this is what I said you need to know if you ever use a library for this. So the distance between zeros is 0, distance between max and infinity is 1, distance between not a number and anything is just infinity. You can't compare this meaningfully. Now, let's talk about limitations. So I already mentioned non-IEEE platforms are an issue, right? If you aren't on an IEEE platform, you can't use guarantees from IEEE standard. This is pretty easy. And I don't mean just some small micro that doesn't even have floating point unit. I mean stuff like IBM. If you are using IBM, by default, it uses its own floats. It calls them hex floating points, hexadecimal floating points, something like this. And they actually, instead of binary digits, use hex digits, hexadecimal digits. And they do their own thing. Luckily, if you find yourself on IBM, I think you can tell it to actually use IEEE floats and get back to rest of the humanity. But you can have issues with IEEE platforms as well. For example, who here has ever had issues because all Intel CPUs had 80-bit computational unit? If you compile for old Intel CPU in 32-bit mode, you will likely generate code that uses the stack-based FPU that actually computes intermediates in 80 bits and then stores them in 64 bits. So suddenly, your computation can have different result based on whether the code you got was forced to store the intermediate result back onto the stack or not. Because you will have different precision in computation and in storage. This is terrible. If you are like targeting Intel 32-bit, please tell it to use SSE for floats. Now, languages. So a lot of languages, for example, C++ and C, actually like don't give you any support for, well, no, they give you support. They don't give you guarantees about the floats. They can be IEEE, they can be whatever they feel like. But even if you have language that says, yeah, this is always IEEE like Go, then you can find that actually like compile time and runtime behave differently. So who here uses Go? Nobody. You are lucky. Actually, I do have to use it for work every now and then. So the thing about Go is that when it does math at compile time, it tries to implement perfect math. It does this like, oh, we just compute it perfectly and then we downgrade it, we round it into the floats. This has some fun issue. What should this print? We have a, set a to minus 0.0. We want to print a and 1 divided by a. So what should this print? I mean, what it should print is obvious. Minus 0 and minus infinity, right? So what does it print? Is the better question. Well, it prints positive 0 and plus infinity. Why? Because in perfect math, there is no negative 0. That doesn't, right? In math, negative 0 doesn't make sense. So the Go compiler goes and goes, okay, so this is constant. So compile time math. Negative 0 at compile time, this doesn't make sense. This is now 0. And so it happily stores 0, positive 0 into your A and breaks everything. But interestingly, actually, like Go does guarantee you that floats are in, do use the IEEE standard at runtime, not at compile time. So let's go to C++. Let's say that we actually write the same code basically, right? We have again some negative 0, we store minus 0 there, and then we take double negative infinity. Oh, sorry, this is supposed to be negative 0 that we divide by. No, this is correct, sorry. So we should have negative 0, negative infinity. So before I show what it prints, who here thinks that this will print negative 0, negative infinity? Okay, we have some votes for yes. Who thinks that this will also print positive 0? No takers. And you are correct. This does do the right thing. We do get minus 0, minus infinity. So what's the issue? Why did I say that C++ also has issues here? Let's change the code a little bit. Notice that we edit constexpr. We now say, okay, but we are at compile time context. And again, we write there the same thing. We want another negative 0, and then we want negative infinity. So what do we get now? Who here thinks that this will print negative 0, negative infinity? Positive 0, positive infinity. We have a couple of takers. Compilation error. Because you can't divide it by 0 at compile time, even though you are in link float, where, this is fine. This is something you can do. It just should give you infinity. You can't rely on anything these days. By the way, if you want to know why, the issue boils down to, so C++ doesn't say what standard the floats follow, right? And at compile time, the compiler has to basically interpret the C++ it supports in expr format. And the committee is not willing to say that the compiler must be able to emulate the floating point model of the target compilation platform, so it just gets to do whatever it wants. Now, that's not all. still C++. You can actually break IEEE standard easily with some compilation flags. Right? If you ever say fast math or fast for MSVC users, all guarantees broken, compiler will start doing whatever it wants. And everything I told you about is a lie. Don't rely on it. Or, just, fast. This sounds like good. We are now fast. But it implies fast math. So again, everything I told you stops working. And there is a bunch of other smaller flags that we can do this. Like fun and safe math optimizations, and so on. Now, this is not all. It can get worse. Your external code, the libraries you are calling, can also break you, just for fun. Let's have the sample of some really evil code, right? It just goes, and it just sets rounding mode, and never resets it. It just says, from now on, all floating point operations will round down. And that's it. Suddenly, everything behaves differently. Incidentally, this means that if you ever write code like this, please first query what's the current mode, and then reset it afterwards. Right? This is useful to be able to change. It's useful to be able to say, I want different rounding, and then get it. But it's a global. Don't touch globals. So you have to reset the state afterwards. Now, to recap. So if you want to do floating point work, you have to know what the guarantees of your language are. And also know when the guarantees stop working. Now, compiler flags can actually break IEEE guarantees. So if you need reproducibility on floats, you have to understand what flags you compile with, and also what flags all of your dependencies were compiled with. And of course, external code can break reproducibility as well. So if you have external dependencies, you ideally need to either audit them, or you need to defensively reset the FPU state that you need every time you are back in your own code. So basically, if you actually want reproducibility, it's a lot of work. But it's useful to have it. Okay, so that's pretty much everything. Thank you for listening. But before I move to questions, I want to show you two more things that are honestly amazing to me. So the first is this fact. You can't constant fold x plus 0 into x. You can't do this. It is invalid optimization. It will break correctness. Try to think about why. And the other one is that you can't constant fold even this, x times 0. You can't say this is 0, this is obvious. This is still invalid optimization that you can't do. Now, it's time for questions. Okay? Yeah, oh, sorry, didn't notice you. Sorry, can you wait? I will come closer.
You said there were 19 values that could mean 0.
Yeah.
So 2 of them are not a number, and 2 of them are 0. What are the others?
Okay, so the question is back to the decimal floats. I said that we have a lot of ways to represent 0. I will try to go there real quick. Just so it is in front of us now. Right, so the question was about when we have something like this, what do we do with the extra representations? Because we can use 2 for infinities, and then we could say use 2 for not a numbers, and what about the rest of them? So there are 2 answers here. One, we cannot care because this is a toy. The actual answer. So this is what IEEE float does, is that you have something like 52 bits in every not a number that you can change. And you can use this to encode more information about the error. So the answer here is that you could pick all the extraneous representations and just assign them different error conditions where you return them. Okay, anything else? Okay, I don't think so. So again, thank you for listening, and let's go enjoy the end of the conference.